feel weird sitting next to this microphone.
All right, let's get started. Thanks for coming to lecture. So today we have, I guess, one exciting development is we're live streaming the lecture in preparation for 2 weeks from now when I guess all of you will be attending remotely. The other thing is we had a quiz planned for next week, which is now not happening. Our tentative plan, as you might have seen on Piazza, but I want to repeat just in case, is that we're planning to hold the quiz remotely somehow on the Monday after spring break. Roughly, we're imagining we'll email you a PDF and somehow expect answers 80 minutes later. We'll figure out the details in a week or so. But that's the plan. Same quiz, just later. And I guess for live streaming, we're planning to use this anonymous question form we had for all of you guys for all questions. So if you're watching live, then you can ask questions, and Franz will relay it for you, or Noah. All right. Any questions about that? Hopefully makes sense. All right. Good. So the actual technical topic for today is we're going to start talking about web security. So this is going to take us a couple of lectures to get through. We'll today start talking about the security of stuff going on in your web browser. And then in the subsequent couple of lectures at this point after spring break, we're going to talk about how the web deals with problems in the network, how do certificates work, and those kinds of issues related to TLS and so on. So to start off this discussion for web security, the problem that we're going to be facing with is one of a user running a web browser on their computer. And the web browser is going to be interacting with lots of different websites over the internet. So you might interact with Facebook, you might interact with Gmail, you might interact with various ads that you're seeing on those sites. You might interact with the attacker as well over the network. The attacker probably also has a website. All these things matter, and there's probably maybe things that you even care about more, like the bank and so on. And the crux of the problem we're going to be trying to talk about today is the fact that the same browser is talking to all of these entities over the network, and there's a lot of stuff running in this browser mixed up from all these different sources. So there's HTML in your browser from all these sites. There's JavaScript code running in your browser from all these different sites. There's CSS, maybe there's Flash, Java, all kinds of complications. And there's sort of a positive and negative here. On the positive side, it's all in a browser, and maybe the browser can do a reasonable job of isolating this whole mess, at least in the browser itself. So if you have stuff on your local file system, then perhaps the browser isn't going to let these web sites access all your files on your computer. So maybe that's true. But the problem is that there's probably lots of important stuff in the browser that you want to protect. Like you want to protect the bank from the attacker. You want to make sure that Facebook, if it's compromised, can't cause your Gmail to be compromised, and so on. So you want to somehow tease all of this apart in your web browser. That makes sense? That's the sort of problem we're tackling for today. And as you've seen from the reading, this is a ridiculously complicated story. It's probably like one of the most depressing readings for the semester. It's like everything is bad and there's almost no hope. And I want to talk a little bit about like what the hell happened. So there's a lot of complexity, and I think it's coming from really two sources here. One is that really the evolution, how we got here, is quite complicated. So initially, when the web was being designed, it was really aimed to support sort of text documents and images. And in that context, it was mostly public information. You were browsing various documents, papers, and so on. Security wasn't as big of a deal. You didn't really have private data or user-specific data. You didn't have dynamic applications as much. And then over time, you saw sort of various mechanisms being introduced. So cookies came around maybe about 4 years after the web was designed. Then JavaScript came around another year later. And you started seeing many more sensitive applications. And what you often see in the web are sort of examples of how the designers didn't really appreciate what the web was going to be used for. So certainly the people designing the web in sort of the text and image era, if you will, weren't really thinking that, oh, every website is going to have a lot of JavaScript and basically be a full-fledged application running inside of your browser, being able to interact with the network and your camera and so on. So as a result, many of the features that you see in the web that we're sort of listing today and other things you saw in the reading were really designed without sufficient security mechanisms in mind. And when we saw, or sort of when the community as a whole realized the security problems, they really had to retrofit security. So many of the security mechanisms you read about feel like, patches. Well, localhost is a problem. Let's patch up some localhost rules. Cookies are a problem. Let's try to tweak that. But one sort of lesson from this is the difficulty of trying to add security after the fact. If you already have a design that you expect to keep working, then making it secure retroactively is a very difficult task. And I think a lot of what you're seeing here is a case study on, well, this is really how difficult it is. Maybe as an aside, one way to view the web security story is really, it's sort of the thing that happened between desktop security and mobile security. So desktop security sort of inherits from 60s and 70s operating systems. It didn't really have a plan nearly even as sophisticated as the web. It was whole users, as we were talking about a couple of lectures ago, and very few security mechanisms that we would want for the kinds of problems we're looking at today. And mobile security, on the flip side, that we talked about last week or two weeks ago, much more sophisticated. iOS, Android have a pretty good plan. And part of the reason why they have a good plan is because the web happened after desktops. They tried to get many more things right, but made a number of mistakes. They didn't sort of foresee where this was going as much. Hard to foresee with this kind of growth. And mobile really learned from the web a lot and had a much clearer plan for security, and you see that sort of working out well. So that's on the sort of evolution side. A lot of the web is complicated security-wise because of the sort of path it took to the present. And now there's actually a lot of constraints you can sort of see maybe related to this evolution, but the fact that you really need to have compatibility. So a lot of the things you saw in the reading were that browser vendors are just not willing to break existing apps. It's important for users for these things to keep working. A number of these things are maybe not as security critical. So even if they keep working in some insecure sense, maybe that's OK. It's just some blog that you wanted to read anyway. Not a big deal if it violates some new policy you're imagining. So very hesitant to sort of introduce functionality that's not backwards compatible. Another is that there's no one really in charge. So there's many browsers that have historically existed. They sort of come in and out of existence, if you will. Chrome is popular now, but Firefox was super popular 10 or 15 years ago at this point. So things shift, and there is nominally a W3C consortium in charge of standardizing the web. And I think recently it's become more of a central focus of how the browser vendors collaborate on setting standards. But a while ago, like 10 years ago, when this document was being written, I think the W3C was not really driving. And what was happening is that browser vendors were independently adding features and trying to get users to use their platforms. And there wasn't really consensus on what the plan was. It was very much decentralized. So that's one other problem. And the other is actually sort of lots of sharing as a constraint. Maybe historically, many of the applications we see in the web have actually lots of interacting components. You have Facebook like buttons and all kinds of websites. You have ads. You have links between sites. You have mashups. And that all is quite difficult to support while providing strong security guarantees. So that's a little bit of an context or aside about why this mess. And probably not a crisp answer, but hopefully it helps a little bit with understanding why we're reading this despite the depression or something. All right, any questions about sort of the context here for web security? All make sense, roughly speaking? OK, so let's talk about a little bit more precisely about the threat model for this lecture's focus, at least. So the kind of issues that we want to deal with for today's lecture really have to do with what's going on inside of this browser box. And roughly speaking, I want to focus on inside the browser box and not on the connections to the various servers over the network. So in that particular sense, I want to assume that sort of the network is going to be OK, but we need to worry about how the attacker is going to interact with other things in our browser. So the way typically people think of this is that we're going to have an attacker, of course, and the attacker owns some domain, like attacker.com or a.com, so I don't have to write as much on the board. And we're going to assume, actually, that the victim, in our case, the victim is the person running this web browser on their computer, they're going to somehow visit a.com. Is this a reasonable assumption? Seems like maybe this is where the story went wrong. Maybe you shouldn't visit attacker.com. What do you think? Yeah?
Can easily be redirected from some other site that looks not like a.com?
Yeah, so I think it's actually really hard to know what you're visiting. So very much for this lots of sharing reason, there's lots of links and redirection and embedded stuff on the web where you might not even know what are all the things you're looking at right now. So it's super cheap to pay any popular website to host an ad there. So if I'm an attacker.com, I can just pay New York Times cents to put up my site on the front page of New York Times. And that just seems like a very easy way to get this to happen. So it's infeasible on the web to imagine this is gonna, we're gonna ask victims not to visit bad sites. This is, by the way, in contrast to other models, like in Android, maybe you could actually have a more expectation in Android of users somehow not installing bad apps, which is much more difficult to imagine in the web context. All right, and the last thing that has to happen is that actually the victim also visits other things, visits important sites. So if it were the case that the victim only visited the attacker's website in that browser, and then used a different browser for the bank and a different browser for Facebook, then you'd actually be in good shape. The browser wouldn't really have to answer any hard questions about what's going on. It's just a browser dedicated to the attacker, a browser dedicated to Facebook, and so on. This would, of course, require that somehow the victim doesn't accidentally go from Facebook to a.com, but it's sort of important to the problem we're going to be trying to solve that the user uses the same browser for sort of most of their interesting browsing here. Make sense? So these are the attack side of the threat model, if you will. What are we assuming is going to happen with respect to the bad guy? There's also things we're not going to sort of worry about. One is that we're going to assume that the browser, in the sort of plus category, if you will, the browser is trusted. So we're going to cook up some plan, some design in this lecture, where I'm going to describe the same origin policy roughly. And we're going to assume the browser has that policy implemented. And in a similar vein, we're going to assume that the browser is bug-free. So it is surely a complicated piece of software, and it surely has bugs. But it's good to really spend time first talking about how is this going to work at all. And then separately, we can do the usual plans for dealing with buffer overflow bugs in the browser C++ code. But trying to tackle it all at once is a little bit nuts. So that's the sort of positive side. We're going to assume the browser is going to execute some plan we're going to cook up. And the thing we're not going to worry about here for this lecture, but we'll talk about later on, is not network attacks. So there are network attacks, and the readings talk about them. But we'll talk much more about roughly HTTPS and things like that in future lectures. Make sense? Questions? That's the threat model. So let's talk about, I guess, what is this plan that we're imagining the browser implementing that's going to keep all these websites away from each other? So this is the same origin policy that you guys read about. And it's kind of a complicated story in a sense. Okay, this whole lecture is going to be trying to present a more principled-looking story for web security and trying to explain some method to this madness that is all the details of web security. And then, of course, the details do absolutely matter. And if you're building a secure web application, you got to understand this whole reading material and probably much more. I think the only reason the web doesn't fall apart is that most websites don't do anything too exciting. And the websites that do exciting stuff, like Facebook and Gmail, really have lots of engineers that are very carefully looking at all the aspects of their design and making sure that it works in all these different browsers in all the right ways. And even then, they probably screw up sometimes. It's hard to have bug-free code. But there is sort of a principal plan here somewhere, and we're going to try to tease it out in the lecture, maybe in ways that are a little bit obscured in the detailed reading itself. All right, so what's the deal with the same origin policy? The rough plan is to disentangle all of those websites inside the browser by sticking them sort of logically the moral equivalent of a process in Unix. So we need some notion of a process inside the browser, or a process-like entity where different stuff from different websites is going to run. In order to identify different units, or like who's allowed to do what, we're going to introduce this notion of an origin. It's going to be all about URLs. So if you have some URL like https foo.com/bar/ I don't know, x.html, we're going to try to figure out some notion of an origin to capture the sort of who is this and who's going to be allowed to operate on this. So the origin is going to extract the protocol scheme, so https foo.com, the domain name, and the port number. So 443 is sort of an implicit port number in this URL, but it's the port number that this server is listening on when it's receiving a request for https foo.com. So when we're talking about the origin, it's a thing you can associate with a URL to start with. And here, the origin of this whole URL is going to be https foo.com 443. The path doesn't matter for the purposes of the origin. They're all in the same bucket. And the plan for the same origin policy is that we're going to take all the stuff that's running in the browser, and we'll sort of informally call those scripts. So JavaScript and HTML, anything that does an action in a browser on behalf of some website, it's going to get an origin. And that's going to represent who is it running on behalf of. So scripts get an origin. And then those scripts are going to do stuff to objects or resources. So the terminology in the web. So a resource is something that a script can poke and do stuff, read, write, request, reload, whatever. And these resources are also going to get an origin to allow us to decide when are things OK to allow or not. And once we're going to assign origins to scripts and resources, then the rule is seemingly very simple. OK to allow a script to poke a resource if the origin is the same. So that's the same origin policy in a nutshell. So a resource might be another page. A resource might be a URL you're trying to request, etc. Make sense? Questions about this sort of high-level view of what the same origin policy is trying to do? All right, so let's look at sort of what this is trying to achieve, if you will, is roughly in the terminology of our picture, that we used to have all these sites sitting on the right. We had Gmail and probably attacker.com. And our browser, in order to keep these guys apart, is going to create two origins here. So one origin is going to be the origin for gmail.com. I'll abbreviate. Probably it's https gmail.com 443 for the port number. But that's the origin for the Gmail stuff. And there's another origin for running all the stuff from attacker.com. And then these guys are somehow going to get connected, and these guys are going to get connected. So then, hopefully, the attacker.com can't poke all the stuff going on in the Gmail window. And I guess these days, tabs are how the windows are rendered. So window is sort of a concept that you see in the same origin policy, and sort of the window is kind of the process equivalent in the web. So in Unix, you have processes. In the web, you basically have windows or frames. And these days, tabs sort of visually represent those things, but the object is roughly called a window in the JavaScript APIs. Make sense? All right, so how is the same origin policy going to prevent anything here? So for example, in JavaScript, a.com can run some JavaScript code here in its window, and it could try to manipulate its own page contents. So it can add, add some text to the page, re-render it, draw whatever it wants. So accesses to the same page are going to be allowed. So some JavaScript code is running here, it can poke its own page. But if this JavaScript code tries to somehow get a handle on the Gmail page and either inject stuff, modify it, or try to view what's being shown in the Gmail page, that's going to be prohibited by this rule, because the script is from a.com, and the resource is the gmail.com window. Not allowed. So it's seemingly having the right effect for us. We're able to prevent bad things from happening. And this notion of a origin associated with a resource is broader than just in the browser. So a very common thing that you might see is in JavaScript code running in a browser, you can request things from the network. So there's a standard API out there called XML HTTP request. I'll abbreviate it with rec. But roughly, you can supply a URL in JavaScript when you're running in a browser and ask the browser to fetch some URL on your behalf. So if a.com does this, it could try to ask the browser to fetch gmail.com, let's say. So if the URL is gmail.com, that is a.com asking to fetch this URL. And the cool thing is, a URL can be translated to an origin by those rules. So the browser can look at this request and say, that's ridiculous. You're a.com, you're trying to fetch this URL from gmail.com. Again, not allowed, but fetches to URLs that are from a.com, that would be OK. So that's how the same origin policy is getting applied in the browser. Everything is about which origin are you part of, both from the code you're running and the resource you're trying to access. Make sense? Questions? Yeah?
There are some websites that try to access legitimately to the other websites, right? And so in order to allow the access, where is the origin, like where are we supposed to measure?
Yeah, so this is sort of the rosy picture, like everything is great, we can cut the world by websites. And in fact, there's a lot of sharing. So the way to think of it is that there's going to be a lot of exceptions to the same origin policy that are going to allow all the sharing going on in the web browser. And those are going to be also sort of the reason why things are hard to secure, because those exceptions have been added in a somewhat ad hoc style or fashion. And as a result, it's difficult to control all those exceptions. So for example, you can create a link anywhere. So it's true, a.com can just poke at Gmail, but a.com can create a link to Gmail, and the user might click on it. Well, OK, so it's not really isolated. You can link. And you could do all kinds of other stuff, as we'll talk about later on. So it's all about these exceptions, unfortunately. So it's good to understand sort of the mindset of the designers of the same origin policy, why they thought this would have been maybe a good plan. That's what I'm trying to explain. Like, it's not ridiculous to think that this might have worked, almost. But then, indeed, a lot of sharing has to happen. And there's exceptions on the browser side. There's exceptions that you can sort of set up on the server side. The server might say, oh, it's OK for me to get a request from a.com because I'm expecting it, and I like a.com in some sense. Yeah, it's a complicated story, indeed. Other questions? All right. So let's talk a little bit now, maybe about what happens on the network, just to understand how the pieces fit together. We're not going to talk about how we're going to solve it quite yet, but important to understand that, so we have this browser. This is all under our control as the designers of the same origin policy, if you will, logically speaking. But then there's all these websites on the right that are not really running in your browser, so these lines connecting to the websites are a little bit, well, not decorative, but they're not being enforced by anything yet. So both sides of that line probably care about knowing where is that connection going to. So if the browser is talking to a.com, the browser wants to know, is it a.com or gmail.com on the right side that I'm talking to? And on the flip side, those sites like Gmail want to know, is this Nikolai's browser or Franz's browser or the browser of someone else? They need to get identified in some way or another. And the answer ends up being a little bit different for these two questions. No fundamental reason why it has to be different. You could imagine the same technical mechanisms applying for mutual authentication on both sides here. But as it turns out in practice, what's sort of worked out for historical reasons is that if the browser needs to identify the server, then what happens, the answer to that, ends up being basically a network encryption protocol called TLS plus certificates that convince the browser that it's really talking to the right server. And sort of this combination of TLS plus search plus some other machinery is what people call HTTPS in the context of the web. That'll be the focus of a later lecture. But the thing that ends up being a little bit more interesting for today is how does the server identify the client? So what I mean by this question is, let's say I'm logically the Gmail server in that diagram, and I receive a request from some browser out there in the world. How do I know it's Nikolai's browser or any other user's browser? And here, it's basically cookies. It ends up being the winning mechanism. For a while, there's been lots of competing sort of answers, like MIT uses certificates very much like for the server identification. This, 15 years ago seemed like a good plan, or 20 years ago. Now, basically, no one else really started using certificates, so MIT is sort of the odd one out, and browsers are trying to phase this out because MIT is like one of the few sites in the world that bothers doing this. So cookies are sort of the answer. There's cookies being sent along with requests that convince the server of which user is issuing a request at any given instant. Make sense? So it turns out that this cookie mechanism is sort of responsible, by virtue of being important to authenticating to the server, has a lot of value. If you can steal a cookie, you can impersonate a user. And the details of how this works out turn out to be one source of a number of security problems in the web. All right, so let's talk a little bit about how cookies work so that we can understand how they fit into this whole picture of keeping the websites apart from each other in the browser. So the way cookies work, logically speaking, is that on the browser end, there's a giant table that the browser maintains. And roughly, there are sort of three important fields in this table. There's the domain of the cookie. And then the cookie itself is like a key-value pair. So key, value, and you might imagine domain is, I don't know, mit.edu, has some cookies set in this browser, where the key is, I don't know, here's my Athena username. Athena is the key, and I don't know, Nikolai might or might not be my Athena username. So that might be a cookie. Not actually any site at MIT that I know of does this, but that's sort of the form in which cookies operate. And the nice thing about these key value pairs is that you can store multiple cookies in a browser for different keys. So different libraries or different applications could share this mechanism. And the way these cookies work is that when your browser interacts with servers over the network, these servers are able to give cookies to the browser. So Gmail, when I first log into Gmail, so the common pattern here is when I first log into a website like Gmail, I'm going to have to log in with my username and password and maybe U2F and other security mechanisms. But once I convince the website that it is me, then the web server is going to give me a cookie. You can think of this cookie, or sort of a session identifier. It's going to be like a short-term password for my account. It's not going to be as good as my full password because the session identifier might expire in a day or so. But the benefit of having this session identifier is I can store it in this table and use it instead of typing in my password every time I click on a link. So that's sort of the cool thing, is that the server can say, here's a cookie, session ID equals, I don't know, some value, and my browser is going to stick it in this cookie table. Gmail.com, session identifier is, I don't know, this thing over here. And then, whenever my browser sends a request to a particular server, it's going to fish out all the cookies from this table with the matching domain name, and it's going to send them over to the web server. So the next time I send a request to Gmail, I'll send this cookie over. And then Gmail is going to let me access my state. And just to sort of complete the picture, when my browser talks to other domains like mit.edu, it'll send this cookie, but not others. Make sense? Questions about this cookie machinery? All right. So again, this sort of looks separable enough. Every domain gets to have its own set of cookies. Things are looking OK. And it's really sort of in the corner cases of sharing and exactly what the policy is that we're going to start to see a number of the security problems crop up with the web here. So what does the cookie security plan look like here? So to a first approximation, you can imagine that the same origin policy is going to apply reasonably well to these cookies. So the origin that we've seen before is going to be roughly the domain of the cookie that our browser is going to be storing. And one sort of source of security problems is that it's, unfortunately, for historical reasons, not quite lining up. So the domain in the cookie table isn't exactly like the origin. So the protocol, whether it's HTTPS or not, is not part of the cookie spec. And the port number is not quite there, and the path is. And it's kind of a messy match. But you can sort of approximate that maybe it's right. And there are a number of security problems that crop up that you saw in the reading that have to do with the mismatch between the notion of an origin, the same origin policy, and the domain and other sort of fields in how cookies get stored and indexed in the browser. So that's one of the problems. But to a first approximation, this does work. And the real problems stem from how these cookies get set and retrieved in that diagram. So the general rule for how cookies get used is that you actually send all the cookies, all matching cookies, on every request. So whenever your browser issues a request to a particular web server, it's going to attach all of the cookies for that server's origin that it is storing. And the important thing here is that it doesn't actually matter which origin triggered this request from the browser side. So even if Facebook creates a link to some other site, or if a.com creates a link to Gmail, when you click on that link from a.com, you're going to be sending all of your cookies to Gmail. That's a little bit fishy. We're going to look at a couple of attacks that show up because of this. And this is sort of, we're starting to see the sharing between sites and the problems that we're going to start having crop up as a result. So that's one problem, which is that these cookies are going to be set very aggressively by the browser whenever it can on every request to every server that you're sending it to. It's only the matching cookies from the right domain, but nonetheless, that's already going to be a problem. And the other problem is answering a question of who can set a cookie. So turns out this question is a little bit, well, browsers haven't always been very good at controlling who gets to set what cookies, and it's still a bit of a mystery, or no, sorry, not a mystery, but kind of an inconsistent set of rules in terms of what the browsers enforce here. And the reason you might care about this, it's a little bit of a subtle question, like what do I care if someone gives me a cookie? It's not my cookie. They already know the cookie that they're giving to me. Should be fine. The reason that this question turns out to be important is a little bit more subtle. So leaking cookies, I think it's easier to see why. The reason that I might care who sets a cookie in my browser is that they might be able to sort of give my browser a session that corresponds to the attacker. So they might log me into the attacker's Google account or Gmail account. And for Gmail, maybe I'll notice pretty quickly, I open Gmail, it's not my mailbox, I'll just log out. But if they sign me into their Google account and I don't use Gmail, I just go to Google to search. And now Google is helpfully saving all my searches in the attacker's account because they're thinking it's the attacker making all those Google queries. So this also applies to a number of other sites where you might just use the site without noticing anything user-specific. But the server is going to collect all the data I'm sending to it in the attacker's account as opposed to my account. And this way, the attacker might learn what Google searches I'm making over time. That make sense? Somewhat of a subtle attack, but nonetheless one that turns out to be one that many of these sites worry about quite a bit. So for example, one question is like, should a.com be able to set a cookie for the domain gmail.com? So it seems like an answer that's probably no. OK, easy enough. Easy enough to answer. What about a.com being able to set a cookie for .com? So one thing I didn't mention here, but you probably picked up from the reading, is that these domains are actually suffixes. So they're like star.mit.edu, star.gmail.com. A.com could set a cookie for basically like star.com. Seems almost legitimate. .com is a suffix of a.com. But this would be a problem, because this would exactly allow this attack, where the attacker site, a.com, gives everyone a cookie setting the attacker's Google account for .com. And then those cookies will, of course, get sent to google.com, because it's part of star.com. Then you're in good shape. Or, sorry, the attacker's in good shape. They're able to force you into their Google account. So why doesn't this happen? Why? What's the rule? How does the browser prevent this kind of stuff? Yeah, back there.
It counts the number of dots in the...
Yeah, all right, so easy enough. That seems easy enough. You know, 1 dot is bad. All right. 2 dots are OK, because like a.com should be able to set a cookie for a.com. But for .com, that seems too crazy. All right, so what about like a.co.uk? Should they be able to set a cookie for .co.uk? Which is like, you know, the .com of England. But the rule said 1 dot. So what's the rule? Like, what's the answer? Yeah.
Manually check for it.
Manually check for what? Yeah.
I guess I assume they have a list of like the domains.
Yeah, so there's actually like a very complicated list indeed. So like the rule can be the number of dots. There's actually a list. It's a fascinating read if you want to read. It's the public suffix list. And it basically lists all the entities that are like .com and .co.uk, where different entities can register domain names under that suffix. So for example, .co.uk is there, but google.com is not, because google.com is all one organization, and they should be able to share cookies. Very complicated list. It's an enormously long list, because like every school district in Massachusetts is in that list, because it's like, you know, k12.ma.us is like an entity on that list, and then different counties in Massachusetts, I think, have different rules, so they appear in the list in different ways. It is a crazy plan. And like some .com domains appear on that list. So for example, blogspot.com, which is a domain used to host different blogs by some company, is in that list, because different domains under blogspot.com are different entities, unlike different domains under google.com. Crazy plan. This is what you get with retrofitting security, right? Like if this was designed with some clean plan up front, you'd be able to have a fairly clear story and cook up some reasonable answer. Any of us could probably design a reasonable story here. But once you sort of commit to how cookies work at some level, it's very hard to recover a sensible sounding security plan afterwards. So every browser ships with this long public suffix list. Anyone can submit entries there. It just keeps growing. And yeah, complicated story there. All right, any questions about sort of this, a bit of an aside on cookie setting? Yeah, question.
Suffix list is packaged into every browser, and then with a browser update, you get a new list.
That's right, yeah. So there's a website, publicsuffix.org, which is the sort of, you know, GitHub-like entity that, you know, manages this list, and you can submit pull requests, and if you prove that you own that domain, you can get it added. So I think for a while, I forget if actually scripts.mit.edu is a thing that should be on that public suffix list. I think for a while they were trying to submit it, but I forget if they succeeded or not. I guess you could check and see if that's on the list. But indeed, these are the kinds of entities that should be there. And indeed, browser vendors, all the browser vendors at least agree on this plan. And every browser vendor, before they ship a binary, they grab the current list from there, make sure it looks OK, stick it inside of the Chrome executable or Firefox executable, and ship it to you. Yeah. Other questions? Yeah.
So you said that like websites like Blogspot
Yeah, well, you're in a bit of a pickle there. Yeah, you don't want to do this. So I think one thing you often see is organizations, like, you really should think of domains as a security entity. And if you're having users host content on a domain, you shouldn't host your content there as an organization. So for instance, I don't know if you noticed, but in Gmail, when you download an attachment, the attachment URL is not coming from google.com or gmail.com. It is actually Gmail giving you a link to download from googleusercontent.com. So it's as if Gmail is redirecting you to some other origin, and that other origin is sort of hosting all the weird attachments. And there's lots of security mechanisms in place to make sure that nothing actually gets, you don't open URLs from there, et cetera. But in the worst case, it is a separate origin, and a separate set of cookies apply, and all this. Same for, I imagine, Blogspot or any of these other companies. If you give a domain to your users, you should pick a different domain for yourself. I think Facebook has a similar property where facebook.com is like the real origin, where all the cookies are stored. And then fbcdn.net is the domain used to distribute all the other user-uploaded photos and all that stuff. And it's like privilege separation in the web. You really want to have a different process, a different UID or different container for your untrusted content. And in the context of the web, that container or UID is an origin. So you get a different domain. And origin sort of host name is not enough because of the cookie problem. So you really have to register a separate .com domain. That's the way to get a separate user ID in the web. If that makes sense. Like the strongest level of a separate UID. You still see lots of historical confused stuff. Like all the sites you see that are all part of .mit.edu, they're not really very isolated from one another. So like WebSys is running in the same .mit.edu domain as all the stuff any of you can host on web.mit.edu. Sure, lots of problems there as well. So not disastrous because there are sort of different gradations. Like the same origin policy applies to whole domains. So student.mit.edu is different than web.mit.edu. But they do share mit.edu for cookies. So probably one of your websites could convince my browser to log me into into your WebSys account. I don't know whether it's good or bad yet, but really should be a separate .com or .edu domain. Question back there.
Is this kind of fixed because we use certificates instead of cookies?
So certificates help to some extent, but if you've noticed, MIT decided certificates are not acceptable for everyone, so then there's this intermediate level between certificates and the actual website. So you use certificates these days to log into this thing called Touchstone or Shibboleth, and then that entity sets a cookie later for the website you actually want to talk to. So it's like, would have been a good answer, but it's sort of lost because your cert convinces this intermediary of your identity, and then you're relying on cookies from then onwards. Now, as usual, man, like every story is more complicated than that, and there's like all kinds of weirdness, but I think this means that we don't get to benefit from search like we would have, like, I don't know, 10 years ago, we would have had a better story, but not as much now, maybe. I don't know how much this matters, but yeah, nonetheless, not a good security practice. All right, make sense? Other questions about cookies? Okay, so let's talk about now some of the exceptions. So far we've sort of described the ideal view of the same origin policy, and there's some mess here with cookies, but things are more or less isolated. And as you asked earlier on, there has to be sharing in the web. And these all take shape of some kind of an exception to the same origin policy. So let's look at a couple of these exceptions, and they're going to translate into various attacks that we're going to be seeing, and I guess have historically been pretty prevalent on the web in terms of adversaries being able to exploit websites that don't get everything right. So let's start out with some easy exceptions in the same origin policy. So the first one is being able to create links. So if you have a website for attacker.com, it's running in my browser. What that means is that my browser is rendering HTML from a.com, and it's running JavaScript from a.com. And a.com could create a link. So this means like a, href, and here's the URL, https, gmail.com, and so on. So already we're seeing that sites can interact. We mentioned this a little while ago as well. The most damaging thing with links is not so much that they exist, but when a user clicks on a link on one website, then the browser loads the target of the link with all of the cookies that the browser has for the link. So if I click on this link in a.com, my browser will load this gmail.com origin in that window or tab, but send all the cookies. So this sends all cookies for gmail.com in making this request. So how damaging is this? Should we be worried? Can the attacker now control that Gmail window, for example? Or not so much? Yeah?
Don't the cookies just go straight to Gmail?
Yeah, okay, so it's like not super damaged yet, which is the cool thing, which is that if I click on this link, it is true that that window is going to send Gmail's cookies to Gmail servers, and it'll like pop up my inbox in that window. But the nice thing is that at the same time, the browser is going to say, aha, this is now Gmail's origin, not a.com's origin. So a.com no longer can poke at this Gmail window that was loaded. So things are working okay-ish. So that's all right. The problem really stems from the fact that this URL might have some side effects. So if it's not a URL that's just load up my Gmail page, but maybe it's like the URL inside of Gmail that deletes all my email, then my browser will load up that URL and send all my cookies to that URL. And that would be damaging if that really happened, that Gmail actually deleted all my messages in response. So that's one problem. Another sort of related issue is a.com could actually load images. So it's sort of understandable why the link exception is there. This is sort of the intent of the web designers. They wanted links. Images are another exception, slightly more dubious, but also some reason why they exist. You could also load an image from a different origin. So I don't know, could load an image from foo.com, bar, whatever. And that is actually allowed. Why do they allow this stuff? This seems ridiculous. Like, why can I load images from anywhere on the web? Yeah? Yeah, so I think the thinking is, well, back then, I don't know, 20 years ago, would have been, well, I guess at this point, 30 years ago, would have been too expensive for everyone to copy images everywhere. So it was important to be able to save on these common images that you could just refer to on other sites. That's a cool optimization. These days, this seems silly. You just grab a copy of the images, and plus your site doesn't break when this other site breaks. But nonetheless, the browsers supported this, and again, the problem is, again, you send all your cookies. So even though you're loading an image, your browser is going to send all your cookies for foo.com in this example to that other server in order to fetch this image, because that's the primitive. When you're making a request, send all the cookies. All right, so how damaging is this? Does this mean that a.com can see can look at any image contents? Can a.com load my Facebook profile picture this way into their page and look at it? No, I guess some shaking of hands. So what's the real story? Okay, can a.com just load up my Facebook profile as part of their page? Yeah, I think they'll be able to, because they got to figure out what's the Facebook URL for that, if there is a fixed Facebook URL, if that's not secret. But yeah, they'll be able to pull up this image. The one subtlety is that actually browsers are fairly fine-grained in this context, which is to say that a.com can display this image in the a.com window, but a.com's JavaScript cannot actually look at those pixels as part of the window. They can look at pixels that came from their own images, and they can look at pixels for their text and other things, but images that came from other origins are now special pixels in their window. Complicated policy. People have gotten this wrong in various ways, but that's sort of the plan, if you will. And if that were at least implemented correctly, then you could imagine that this is kind of cool. a.com is able to load images from anywhere they want in the world, display them to the user, but not be able to leak them to a.com itself. And seems almost like a reasonable plan. As you can imagine, things over time shift. So for example, this used to be exactly true what I said. And then people came out with CSS and various layout tricks and control of layout on the page. And what happened is that now the code of a.com can actually see the layout of their window. And as a result, they can see the dimensions of this image, but not the content. So this is becoming a kind of a weird security policy, which is that a.com can see the dimensions of any image I'm allowed to load. So people have used this for various sort of subtle things, like if I have some bank account and I request an image of, like, I don't know, some diagram showing how much money I have or something like this, then that image might be different size depending on what's going on or which accounts I have. And they can tell how big the image response was based on how it was rendered in their page. Crazy attacks, but people have tried to take advantage of this stuff. Yeah?
If you have like multiple images of the same dimensions, how does it know that it's like a valid image?
Let's see. So what's the it that you're referring to there? So you're supposing some situation where there's an attacker.com window open in my browser, and it might be loading different images that are of the same dimension. Then it can distinguish them. Then the attacker.com can distinguish them. The browser is going to render them all in my window, in my screen, and the attacker.com can't tell which of these equal dimension images are loaded. But if they're different dimensions, now they can tell. And depends. If there's a confidential website that you're using where there's important images that are of different dimensions, well, you shouldn't do that on the web. It's like a subtlety, but or like depending on how much exactly you care about that. But like here's like a weird thing you got to keep in mind if you're trying to maintain web security because of this exception. Yeah, make sense? Other questions? All right, so those are two exceptions, and already we can start to see how you might have a bit of a problem. So here's an example attack that's pretty popular. I should say, actually, like Lab 4 that you guys are going to do in a couple of weeks is all about web security attacks. So in Lab 4, we're going to give you guys sort of the Zubar website, which is full of these vulnerabilities and on the website. And your job is going to be to craft various attacks using HTML and JavaScript to sort of steal cookies and inject cookies and what have you. So here's one common flavor on attack. The web guys are very good at acronyms and terms. So this attack that I want to present is called cross-site request forgery. And it abbreviated CSRF. And it sort of follows the lines we've been talking about, stems from the fact that your browser will always send cookies to every request, regardless of which origin actually initiated the request. So here's the sort of picture to have in your head. You have a browser in your computer, and you're logged into some bank website, your Gmail website, etc., and you visit a.com. So a.com is going to send you some HTML page, and your browser is, of course, going to run it inside of a.com's origin. But that page has an image tag. So it says image source equals bank.com slash xfer to transfer some money. Here's the amount, $500. And by the way, recipient is the attacker. All right, so that's a valid image tag. So what's going to happen when your browser sees this? Well, it's going to request something from bank.com. It's probably not going to get an image back, so it'll display something kind of broken, like, I don't know, an empty box or a broken image tag in your actual window. But on the wire, what's going to happen is that your browser is going to issue a request to bank.com over here. And the request is going to be for the URL /transfer, amount equals this to the attacker. And by the way, it's going to be accompanied by all the cookies that your browser has. So it might say, the session ID is such and such. And if it happens to be my current session ID with the bank, then from the bank's point of view, you can sort of see this network request coming in. It doesn't really say anything about a.com. It's just a request to do this transfer with this set of cookies that correctly identify a user. Seems like exactly the way that a legitimate request would have come into the bank. Question?
This is like the request, like a get request.
Sorry. Yeah, OK, so one thing is indeed. So this is a get request, so that's one thing. Indeed, so it's a get request to /transfer. Turns out you can make a post request too, not a big deal. But indeed, yeah, you had a question too?
Like this only works if it's if like bank.com like codes this endpoint as a GET request, right?
Yeah, right. So this ends up being the case for GET requests. You can make this happen for POST requests too. It's just slightly more complicated. So if you wanted to issue a POST request, what you would do is you'd create a form. So you'd create, let me try to improvise on this. Inside of that a.com box, instead of the image tag, you just say, form action equals bank.com/xfer. And you can have all the input fields here, hidden value, or input type hidden value such and such. And then you could say, here's the button, submit, or input type submit, whatever. And from JavaScript, you can synthetically submit forms. So in JavaScript, you can say, click this logical button. And it'll be as if the user really clicked this. So that will generate exactly the same request we had on this diagram, except that instead of a GET, it'll be a POST, because forms POST. So you can make a POST like this just as well. So the POST sort of versus GET convention is useful for other things, but doesn't save you in the security context. It's not like the browser prevents a.com from issuing a POST, but allows a GET. All right. So how damaging is this? Basically anything where the server cares now whether a user really issued this or not, sort of suspect. Because any request you get from the browser, you can't actually tell what happened. So this is a situation where you could have imagined lots of potential fixes. Like maybe there should have been a header. Like, yeah, you are getting the cookies, but by the way, this is a.com causing this to happen, not bank.com. Or you could have had a different rule, like if it's cross-origin, you don't send the cookies, etc. Some of these fixes have been sort of available in various extensions to the web security. Like one of the optional reading we assigned for this lecture actually has a list of these things. And one of the features that modern browsers support, I think all of them at this point, is a thing called same-site cookies. So that's basically a cookie that is not sent by default when other origins try to send a request. So here, all the places where I've said that your cookies send with all their matching requests, the exception is that modern browsers extend this cookie table and have an extra column that says, this is a same-site cookie. And if it's a same-site cookie, it'll only be sent if that domain is causing the request to be sent, and will not be sent in all these crazy cases like this. So if the bank was expecting this to be sort of set this cookie as a same-site cookie, then this cookie would not be specified here, then you'd be good. Question?
The default.
Well, lots of things break. So for example, the Facebook like button doesn't work in that world. Because you can't click like because you're coming from a different page. And links almost don't work. So like if you have a bookmarks page and you want to bookmark Facebook, then you click Facebook from that link, you go to Facebook, but without your cookie. So like every time you click a link to Facebook, you will be taken to the Facebook login page. You're not logged in. Then you reload it, then you're logged in because, well, now maybe you're like within Facebook. All kinds of things just break because they were assuming this was going to work. So I think that's the thing. So many of these measures you could take at the cost of breaking lots of existing sites. I think that's sort of where the web is. Like many, as we were talking about, it's really this backwards compatibility that's causing a lot of these problems. But at the same time, it's cool. Like the web keeps working. I don't know actually what I'd prefer. Like if the web was broken every year, that'd be also disappointing. Yeah. All right. Other questions about this sort of problem and the same-site cookie solution? It's kind of cool. Works. You got to name your cookie in a particular style and set some flag on it. Then works pretty well. All right, so let's talk about how we might actually defend against this style of an attack. So I don't think I need this. So let's talk about defenses for this cross-site request forgery attack. All right, so the usual plan to defend against CSRF attacks is going to take the form of having some kind of a secret that a.com cannot get. So in order to send this request, previously, you needed the secret cookie. But the secret cookie wasn't really being kept secret by the browser, so we're going to add an extra secret, a second secret called a token that's going to really make sure that it was from bank.com and not a.com. So here's how this is going to work. So we'll have our website here, bank.com. And the websites now are responsible for storing extra state to deal with this CSRF problem. So the server is going to store a table of all the users and some kind of a randomly generated token for that user. So maybe for Nikolai, it'll say, well, the token is 152, and for every user, there's another different random token. This is in addition to the usual cookies and passwords and all the stuff that you're already going to have. So you're going to store this extra CSRF token for every user on the server. And then the rules are going to be that the request, in order to transfer money, has to be, XFR like before. You need an amount and a to field, and you need to specify this token. And this token value specified in the request to transfer money better be exactly the token that's stored in this table for the particular user whose cookie is attached. So it's the XFR request and the cookies sent along and all this stuff. So the browser now, so here's our browser on the client side. It might, again, have our attacker.com running stuff in the browser. And bank.com is also in the browser, has a cookie and has a separate window. So why is this going to work well? So when the bank renders a page, when you log into the bank and you get a form to transfer money, the bank is actually going to send you an HTML page here, like some kind of a form, like we were talking about on this board back here. This form was going to allow you to type in how much you want to transfer and to whom. And one of the fields in the form is actually going to be a hidden field with this token value equal to whatever is stored in the database for your username. So when the bank sends me the page in the first place, it fishes this random value out of the table. And now my bank.com window has this as part of the form. When I submit it, it'll go to the server. The server will check, all good, allow the transfer. When a.com tries to pull off the same attack, so the a.com server can synthesize almost all of this, but it doesn't know the secret value. It knows the secret value for the attacker's account, but I'm not logged in as the attacker. I would send my cookies. So the attacker's guess for this token value isn't going to be valid. And if the attacker somehow uses their cookies, then, well, that's fine. It's the attacker's bank account. I don't care about transferring money from there. So it really relies on the fact that the secret value is going to be supplied in the legitimate transfer page and not available to a.com when they're trying to set up this link on their own to trigger the stack. Question?
Is it possible that the attacker page can download the real legitimate page, get the HTML, parse out the token, and then put it into their
Yeah. So of course, this is the thing to worry about. And the reason this doesn't work out for the attacker is that this token is different for every user and is only displayed when that user is logged in. So this is like a secret value. It's actually really sensitive, as you can imagine. And attackers cannot get this value unless they're logged in as you. If they're logged in as you, it's game over for other reasons. They can just log in as you and do whatever they want. But if they're not logged in as you, if they can't request your page from the bank will not serve them this token value, and then they can't get it.
But couldn't they send a request on your behalf through XML?
Okay, yeah. So exactly right. They could send JavaScript code here that will do an XML HTTP request to bank.com's top-level page. And now we come back to this picture. A.com could initiate this request, but the URL in HTTP request is different origin. And the browser is going to say no. You can create a link, and it'll open the bank in a new window. Then you'll have the right token, but then you'll have lost control of that page. It's like the example we had before, where the attacker.com can give you a link to Facebook. It's a very subtle attack, and there's ways to screw this up, actually. So the reading talks about things people have tried in the past that didn't work out very well. So let me get this question, and I'll come back to the broken thing.
Is this something that was implemented as something to be backwards compatible,
This scheme? Well, this is basically a scheme that web applications had to cook up because the browsers were there, people were buying stuff online, they were using banks online, and all of a sudden people realized, well, that's unfortunate. What are you going to do? You can't wait for a year for a new browser to ship. You've got to figure out how to make this problem go away in the current set of mechanisms. So they figured out how to use the current set of mechanisms, which is like, I don't know, extra fields in the form and so on, to make it work. And sort of it stuck around. That's right, yeah. So the cool thing is that we're able to actually introduce this patch, if you will, purely above the browser level. The same machinery as far as the browser is concerned. This is just a different way of writing a web application. And web applications are full of these kinds of tricks. Like the browser has a certain API, and to build the correct web application requires you to jump through, like, I don't know, 50 more things like this. And the reason that many web application developers don't run into this is that they use some framework, like, I don't know, Node.js or many frameworks out there. I don't know, Django was a popular one. I don't know if it's still around. React, all these things. Those take care of a lot of these details for you if you use their abstraction for, let's have a form. So in Django or in React or some of these things, you say, oh, I want a client-side form. It'll automatically do all this stuff for you, like set up a table, add these tokens, check the token on response. All the stuff is happening under the covers. And similar things are happening for making sure cookies are same side, and yeah, lots of details are being papered over by various frameworks. That sort of works out. And if you have a particularly important website, you now have to be an expert in this stuff, because if there's one thing the framework forgot, it's your problem now. So, there's a sort of a really high cost. If your job is to build a really secure web app, then all of a sudden you must be an expert in all these corner cases in this tangled web book. That's a little bit bewildering, yeah. Yeah, so the other scheme I was going to describe for dealing with cross-site request forgeries is that people have previously thought, well, it's kind of a bummer if the bank has to store this extra table and update it every time and do lookups. Why don't we just stick this token into a second cookie? So we'll have two cookies, the session ID cookie and the expected correct cookie. And if the expected correct, sorry, the cookie containing the expected token matches the token that you actually get in the request, then we're good. Sort of virtualize this table from the server and push it out into cookies on everyone's browser. And the reason this didn't work out so well is because the attackers figured out that, well, maybe there's some way in which I can inject my chosen token into the victim's browser, and then I know what token to supply in this fake request because I just injected that cookie for you. So this requires that some of these cookie problems that we were talking about before, about the attacker being able to inject a cookie into various domains, actually work out in the attacker's favor. But if that works out in the attacker's favor, then all of a sudden, the attacker can bypass the CSRF defense. So that's sort of more an example of how little details really matter hugely. And this scheme is the one that pretty much every site uses these days, and as far as we understand, seems to be actually a pretty good plan. Make sense? Other questions? All right, so let's talk about another exception to the same origin policy that turns out to be pretty important. This one has to do with JavaScript code itself. So here's another same origin policy exception having to do with script tags. So this is how you supply JavaScript code, or one of the ways you can supply JavaScript code as part of your page. So the question is, what happens if a.com, like we had before, can have a script tag that says, script source equals, I don't know, foo.com/library.js. So what happens? Well, one thing that's going to happen is, OK, the browser is going to load this. And actually, browsers in the same origin policy have an exception for scripts, very much like they do for images, which is to say that even though this is requesting a resource from a different origin, foo.com, not a.com, this is going to be allowed. So the browser will load this URL, and then it'll actually run this JavaScript code. Here's the next question. Where is this running, this JavaScript code? What origin is this code now running with? Is it running as foo.com or a.com? Any guesses? Yeah.
Presumably a.com?
Yeah, so I think the intuition to have for why a.com is that this is kind of like using a shared library or calling into some copy-pasted code that you had. This code might have come from somewhere, but that doesn't matter. You're currently running it in your process, very much like in Linux. If you're running a process and you're calling a library, it doesn't matter that someone else wrote library. Library is in your process, in your address space, has all the same privileges. So in the same vein, this JavaScript code is now going to run in the a.com origin. If this has some bug or vulnerability or some malicious code, it's going to be able to take over a.com. So like in running library code in a Unix process, you should be prepared to fully trust all the libraries you're loading into your program. So that seems important. Here's another question. So in the image case, we were worried a little bit about whether a.com was going to see the contents of the image. So up there, yeah. We were thinking, OK, well, a.com could request any image it wants. But we had this plan saying, well, that's OK, because we're going to display the image, but not let a.com look at the pixels of the rendered image. Maybe we're going to leak the dimension, but that's it. What's the deal here? Can a.com look at what the code is here? Well, kind of. It's a little bit weird, right? Like, they certainly don't get to see the literal ASCII representation of this code, but this thing is going to run in the address space of a.com. And JavaScript have all kinds of reflection features. Like you can say, what are all the functions defined here? What's the body of this function, and so on. So you can't get literally the contents of this JavaScript page, but you can infer a lot about it. So here's another weird exception, which is that if you have some secrets, they better not look like JavaScript code. Because otherwise, an attacker could do this trick to load what your secret might have been. Might not be great JavaScript code, or may not parse exactly like JavaScript code, but if it accidentally parses anything related to JavaScript, the attacker will be able to load it up and then examine what's all the code on my page, and then learn what this secret value was. The reason this was going to be secret is, of course, like everything else, this gets loaded with all your cookies, even though it should be just a library. So a sort of a stupid but kind of a cute trick is that many pages, or like a recommendation, I think still a reasonable one today, is that if you have some data that you expose that can be fetched by just providing cookies and not providing any CSRF token like this, your response should probably start out with something that makes the JavaScript interpreter infinite loop. So one thing is, if you are ever serving data, so OK, so here's maybe an example. Suppose that Gmail exposed my list of attachments, or like the Gmail app itself needs to fetch how many messages I currently have. So here, messages. It's a URL that my Gmail app fetches to get the current messages. The Gmail app uses XML HTTP request to fetch this. Everything works out great. What if the attacker tries to load this as a script? Well, if accidentally this looks like JavaScript, or like one of the subject lines of one of my emails is a JavaScript expression, a.com can get it. So one sort of stupid trick that I was referring to is that the response to this should start out with something like, while true, keep looping, and then here's the data. And this stupid trick sort of avoids this problem, which is that if any browser tries to load this page in a different origin and run it as JavaScript, that page will immediately freeze at this statement and not be able to do anything else with the data. And the legitimate requester, gmail.com, can request this URL through a different mechanism, not script source, but XML HTTP request. And there they can just say, oh, well, skip the first line. We know that's silly. Then go to the data. So this is sort of to yet another silly-looking example, but this is what it takes to deal with these security policies that weren't designed well from the start to isolate. And you really have to worry about all these exceptions. So like as we were saying before, with images, better not be that any of your secrets are related to image dimensions. Better not be that any of your secrets are in executable JavaScript form. And like CSS is another thing like this, and so on. So complicated world to isolate. OK, so that's sort of important to understand. But here's another attack along the lines of CSRF that's going to be good to know about, especially for the lab. And this attack is called cross-site scripting, or XSS. Here's the sort of worldview for this attack. Instead of having a.com be a website that the attacker owns, we're going to have now a setup where the attacker doesn't actually need a website at all. And the attacker is going to be a user with a browser. We'll have some shared server like Facebook, even though I don't want to pretend like Facebook necessarily has these bugs, but they've had in the past. So what's going to happen is that attacker's browser is going to send some request to Facebook. In order for this attack to work out, what's going to have to happen is that the website is going to have to share data between users, so like posts in Facebook. So this user might post an article to Facebook whose contents or text is your script source something. And if Facebook takes this a little too literally and doesn't do anything sophisticated, we're going to imagine that the victim here comes along with their own browser and asks the Facebook server for the list of postings. And what Facebook might send back now is, well, here's a new post, script source, whatever. And now, from the point of view of the victim browser, Facebook just sent the script source tag. The URL here doesn't have to be Facebook. We saw the rule is you can refer to any code. And it runs in the Facebook origin. So the good thing is it's isolated to Facebook. It doesn't take over your whole computer. But the attacker, by supplying a URL to their code of choice here, gets to then control what JavaScript code is going to run in your victim's browser in the facebook.com origin, which might be a somewhat sensitive origin depending on what's going on there for your account. So now what's going on is that Facebook failed to sort of notice that they're accidentally sending this instruction to their victim browser. Make sense? Questions about the attack setup and what's going on? So there's many ways in which you could sort of imagine or like blame what happened, or like many things you could have done differently that would have prevented this attack from happening. So if we said that the script runs in a different origin than Facebook's, then okay, then story would have been different maybe. If we prohibited these scripts, story would have been different. All those things aren't quite how the world works because people didn't get to change the browser quickly enough to deal with these attacks when they were discovered. So what people do for these XSS attacks is really, well, you can imagine. One thing is sanitize, or like no tags allowed. No tags in comments. So if you ever have user-supplied data that's part of your web page, maybe you should just restrict it to, alphanumerics and space, something extremely limited. Then you can't have angle brackets, you can't have any tags. That's OK. Turns out to be problematic because users do want to have formatting. Slightly more sophisticated and slightly more risky scheme is to actually filter tags. So you might imagine that, well, we should say, well, you're allowed to have like bold or italics, but not script. This turns out to be extremely difficult to pull off because there's many places in HTML that you could embed JavaScript code. It's very difficult to figure out what browsers will execute, and I think the Tangled Web talks quite a bit about some of these problems. The other thing that people do is there was this attempt for a while to have a notion of HTTP-only cookies. So why is this even a thing that shows up here, and what does it have to do with defending against cross-site scripting attacks? So the context for HTTP-only cookies are cookies that will only be sent on requests from your browser to the server, but not available to JavaScript running in your browser. And the reason this seemed like maybe a good idea is because what attackers did with this XSS bug is they injected code into facebook.com that would take the victim's cookie and send it to the attacker through one of those CSRF-like attacks. And then if the attacker has your cookie, then okay, then they basically have your account, easy enough. And HTTP-only cookies were thinking, well, we'll be clever. You can't get the cookie from JavaScript. You can only send requests to the server. And this like helps, but only a little bit, because the attacker can still inject all the things they want to do right into this page and get your browser to send all the requests on the attacker's behalf. So this is a partial defense. And sort of the other thing that people have developed much later on. So these are the things that sort of people really did when they got bitten by XSS. This was the first attempt to like fix the web. Didn't really work out as well, or like didn't really address the whole problem. Now there's this thing called the HTTP Content Security Policy, or CSP. And this is basically an opt-in mechanism by which a web application or web page can set a special header in the victim's browser saying, Facebook.com is not expecting to send you any things like this. Ignore them if you get it. Along these lines. So you can, for example, in the CSP policy, you can say, only run JavaScript code served from these particular origins. Don't load JavaScript libraries from elsewhere. And there's a long list of other settings that you can opt into with the CSP plan that improve the security of the browser against a number of attacks like this. This has been a pretty, I think, successful plan. Many websites opt into it. As usual, a complicated site like Facebook might have trouble opting into it right away, which is why it's not enabled by default. But it's a pretty nice mechanism. Questions? All right, so that's a sort of summary of web security. It's sort of an interesting case study, as you see, between trying to, it's like an extremely successful system, extremely widely used, but has had an interesting history of security problems, and this is how many successful systems evolve. I imagine maybe mobile security in 10 or 20 years is going to look like this, with messy security solutions to problems we don't really understand now. But it's sort of insightful to see how people have nonetheless made it work in some way or another. All right, so I guess see you guys online from now on.